From precision transport to complex installation, massive wind turbines rise in harmony, transforming open landscapes into a powerful, inspiring wind farm renewable. The dream of a wind power field rising from the white sand dunes of Le Thuy, Quang Binh is gradually becoming a reality. We witness the challenging transportation of massive wind power equipment across endless stretches of soft sand and harsh coastal terrain. Every journey is a true test of engineering skill, teamwork, and determination. Day and night, the Lienman LMT team works tirelessly, carefully guiding long convoys through narrow routes carved between sand dunes. Heavy transport vehicles move slowly and steadily, overcoming unstable ground, strong winds, and difficult weather conditions. Each turn, each meter forward requires patience, precision, and absolute focus to ensure the safety of both equipment and personnel. Despite countless obstacles, the team remains committed to their mission. Every successful delivery marks another step toward clean, renewable energy for the region. This demanding operation not only showcases technical capability, but also reflects the perseverance and dedication behind turning a bold vision into a sustainable future for Quang Binh. The careful unloading of 18 massive L160 wind turbine rotor blades, each designed for next-generation onshore wind power projects. Using heavy lift port equipment, the blades are discharged one by one from the barge with millimeter-level precision. Specialized lifting frames and experienced crane operators ensure that the long, slender structures are handled safely, avoiding torsion or surface damage during every movement from vessel to quay. This discharge operation is part of a larger logistics campaign organized by Hanseatic Breakbulk, HBB. Between May and December 2021, HBB successfully arranged 8 consecutive tow voyages, transporting a total of 144 L160 rotor blades from Poland to Cuxhaven. The transports were carried out using the tugboat Wolf 7 inches in combination with the heavy-load barge Todue 3, a setup well-suited for oversized and sensitive cargo. In total, the overall project includes 180 rotor blades, all destined for the Southeast Wind Farm project in Dak Lak Province, Vietnam. This project represents one of the largest and most advanced onshore wind developments in the Asia-Pacific region. With a total installed capacity of 400 megawatts, the wind farm will combine 98 E138 turbines and 60 E160 turbines, equipped with the latest EP5E2 technology. The E160 turbine, featuring a 5.5 megawatt single-speed generator, is capable of producing up to 21.5 gigawatt-hours of electricity annually, significantly contributing to renewable energy generation. The precise discharge operation in Cuxhaven is therefore a critical link in a global supply chain that supports Vietnam's transition towards sustainable and high-capacity wind power. The Liebherr LG 1750 mobile lattice boom crane plays a vital role in modern wind turbine installation, where extreme lifting capacity, height, and mobility are all essential. Designed as a specialized all-terrain lattice boom crane, the LG 1750 successfully combines the advantages of wheeled mobile cranes with the high load capacity typically associated with crawler cranes. This unique hybrid concept makes it particularly suitable for large wind energy projects spread across wide and often challenging terrain. With a maximum lifting capacity of approximately 750 metric tons or 850 US tons, the LG 1750 is capable of handling the heaviest turbine components, including tower sections, nacelles, and oversized rotor assemblies. Its impressive lifting performance allows operators to safely and precisely position components at extreme heights, reaching a maximum hook height of up to 193 meters or 633 feet. This capability is critical for installing today's increasingly tall wind turbines, which demand both stability and precision at height. One of the crane's key strengths lies in its flexible boom system. The LG 1750 can be configured with various lattice boom combinations, enabling it to adapt to different turbine sizes, site layouts, and wind conditions. This versatility reduces setup time while maximizing operational efficiency on site. In addition, advanced control systems assist operators in maintaining smooth and controlled lifting movements, even under high loads and long boom lengths. Powering the crane is a robust 8-cylinder, water-cooled diesel engine delivering 686 horsepower. This powerful drivetrain ensures reliable performance during demanding lifting operations, while maintaining consistent hydraulic output. Despite its enormous lifting capabilities, the LG 1750 is engineered for economical mobility. The crane can travel between job sites with several components already installed, keeping transport costs low. Typical axle loads are around 12 tons, allowing it to move on public roads with fewer logistical constraints compared to larger crawler cranes. In wind turbine construction, where efficiency, safety, and mobility are decisive factors, the Liebherr LG 1750 stands out as a highly capable solution. Its combination of massive lifting power, exceptional reach, and cost-effective transport makes it an indispensable machine for the installation of modern wind energy infrastructure. The transport operation begins as the heavy convoy slowly sets into motion in Koprivna, Czech Republic. A massive wind turbine tower section rests securely on a specialized multi-axle trailer, carefully balanced and fastened. Under the direction of experienced operators, the prime mover pulls forward at a controlled pace. Escort vehicles move ahead to secure the route, while personnel monitor clearances and road conditions. The convoy advances cautiously through the village, navigating tight turns and uneven surfaces. Every movement is deliberate, as the sheer size and weight of the tower section demand precision, coordination, and constant communication from the moment the journey officially begins. In the world of heavy industry and oversized logistics, NC Nielsen stands out as a leading provider of advanced heavy-duty solutions designed to handle the most demanding loads. The video highlights a comprehensive portfolio of powerful machines engineered to move extreme weights with precision, safety, and efficiency. At the center of these solutions is the NCN 152T reach stacker, recognized as the world's largest reach stacker. With an impressive lifting capacity of 152 tons and a load center of 300 millimeters, this machine is purpose-built for handling exceptionally heavy and oversized components. It sets a new benchmark for reach stacker performance in ports, industrial sites, and wind energy logistics. Complementing this flagship model is a full range of high-capacity reach stackers, including the NCN 85T, NCN 100T, and NCN 130T. These machines provide flexible solutions for different load requirements while maintaining high stability and maneuverability. Their robust construction and advanced control systems ensure reliable operation even in confined or challenging environments. A key application shown in the video is the transportation of wind turbine towers, weighing up to 140 tons. Using specialized equipment such as the combi-lift gantry, NC Nielsen enables precise lifting and positioning of large cylindrical tower sections, which are critical components in modern wind farms. For even heavier transport tasks, surely modular transport solutions are presented, capable of moving loads of up to 430 tons. These systems are designed for extreme heavy haulage, offering modular flexibility and unmatched load distribution for large industrial components. Together, these heavy-duty solutions demonstrate NC Nielsen's commitment to innovation, strength, and reliability, supporting industries such as renewable energy, ports, manufacturing, and heavy engineering worldwide. The construction of foundations for onshore wind turbines is a critical stage in ensuring the stability, safety, and long-term performance of the installation. At Glenouth Wind Farm in County Tipperary, Ireland, this process involves creating massive reinforced concrete structures capable of anchoring turbines and effectively transferring loads to the ground. Typically, these foundations take the form of either large gravity slabs or piled systems, with the choice depending on turbine size and local soil conditions. The construction process begins with site preparation and design, during which engineers analyze the geotechnical conditions and determine the required type and depth of the foundation. A reinforced gravity base is often preferred when soil conditions allow, while piled foundations are adopted for weaker subsoils. Once the design is finalized, the site is cleared, leveled, and marked for excavation. Next comes excavation, where earth is removed to the required depth and width, creating the cavity for the foundation. This step is carefully monitored to ensure proper alignment and stability. Following excavation, the reinforcement phase is undertaken. A dense network of reinforcement bars is placed, along with a steel anchor bolt cage that will later serve as the critical connection point between the foundation and the turbine tower. This cage is positioned with precision to maintain alignment for tower installation. The most crucial step is concrete pouring, where high-strength concrete is delivered and poured into the foundation cavity. For large foundations, continuous pouring is often performed to avoid cold joints and ensure uniformity. Once poured, the concrete is compacted and leveled to form a solid mass around the reinforcement and bolt cage. Afterward, the curing process allows the concrete to gradually gain strength and durability. Proper curing ensures the structure can withstand the immense static and dynamic forces generated by turbine operation. Finally, once curing is complete, tower installation begins. The turbine tower base is securely bolted to the embedded anchor cage, ensuring a firm and lasting connection. Through these stages, the foundation provides the stability required to support wind turbines, enabling the reliable production of renewable energy at Glenouth Wind Farm. At Dagebull, a key milestone in renewable energy development is achieved with the installation of a 3.4 megawatts SN wind turbine, carried out using our powerful Liebherr LTM 1750-9.1 mobile crane. This project highlights the precision and expertise required to erect modern onshore wind turbines with a hub height of 80 meters. The operation begins with careful site preparation and crane assembly. Thanks to its 9-axle design and exceptional lifting capacity, the LTM 1750-9.1 is ideally suited for handling the heavy and oversized components of the CNC turbine. Once positioned, the crane lifts the tower sections sequentially, ensuring perfect alignment and stability at each stage. Next, the nacelle is hoisted to the top of the tower, a critical lift that demands absolute accuracy and constant communication between the crane operator and the ground crew. Finally, the rotor and blades are lifted and installed, completing the main structural assembly of the turbine. Throughout the process, safety, efficiency, and coordination are top priorities. Despite challenging coastal weather conditions, the installation proceeds smoothly, demonstrating Kranz-Solar GmbH's experience in wind turbine erection. The completed 3.4 megawatts Senvion turbine now stands as a strong contribution to sustainable energy generation in the Dagebull region. The installation of wind turbine blades is one of the most critical and visually impressive stages in the construction of a wind power plant. Due to their enormous length, weight, and sensitivity to wind conditions, this operation requires the use of powerful cranes, precise planning, and highly coordinated teamwork. Before lifting begins, the crane is carefully positioned on a reinforced working platform to ensure stability under heavy loads. A main crane with a long boom and high lifting capacity is typically used to handle the blades, while auxiliary cranes assist with rigging and blade control. Each blade, often exceeding 70 meters in length, is transported to the site and attached to specialized lifting equipment designed to prevent structural stress or surface damage. During the lift, the crane slowly raises the blade from a horizontal position on the ground into the air. Taglines are used by ground crews to control rotation and maintain alignment as the blade is guided toward the turbine hub at the top of the tower. Operators must work with extreme precision, as even small movements are magnified at such heights. Wind speed and weather conditions are continuously monitored, and lifting is paused immediately if safety limits are exceeded. Once the blade reaches the hub, technicians secure it using high-strength bolts and calibrated torque tools. This process is repeated for each blade, until the rotor is fully assembled. The successful installation of wind turbine blades demonstrates not only the lifting power of modern cranes, but also the high level of engineering accuracy and safety management required in renewable energy construction projects. Wind turbine maintenance is demonstrated as a careful and closely coordinated operation, relying on a large crane. To access critical components, the crane is positioned next to the tower and slowly lowered to the ground. Throughout this process, the technical team works with utmost care, using clear hand signals and maintaining constant communication to guide the crane operator. The turbine is lowered slowly, ensuring stability and safety at every stage to avoid sudden movements or structural stresses. After the wind turbine is safely placed horizontally on the ground, technicians begin the detailed inspection and maintenance process. Critical mechanical components, such as the gearbox, shaft, braking system, and couplings are carefully inspected. The video highlights the serious consequences of inadequate maintenance. If critical components, such as the shaft brake, are not replaced in a timely manner, the damage can become much more severe. In this case, the rotating shaft gear was holding the coupling instead of braking, leading to damage to both the gearbox and the main shaft. This example clearly illustrates why proper and timely. The construction process of the wind farm begins with extensive foundation preparation on the mountain ridges of Pelton, Rizal. Each turbine site is carefully surveyed, excavated, and reinforced to create massive concrete foundations capable of supporting the tower and withstanding strong wind loads. Meanwhile, the main turbine components, including rotor blades, nacelles, and segmented steel tower sections, arrive at the ports of Manila. From there, the equipment is transported over long distances through Manila's congested urban roads before continuing along narrow, winding mountain routes leading up to the project site in Rizal. This logistical stage requires detailed planning, traffic coordination, and specialized transport vehicles. Once on site, construction teams begin erecting the towers. The tower sections are lifted and assembled vertically, followed by the installation of the nacelle and rotor blades. This process is repeated for all 27 Gamesa G90 turbines, each with a capacity of 2.0 megawatts, gradually transforming the landscape into a fully operational wind farm. The offshore wind turbine is installed using a floating installation vessel, where precise motion control is critical. During the operation, GeoDelph deploys 13 sensors to measure vessel movements, creating a single dataset to validate motion compensation models for floating installations. To install the blades, a specially designed guide is wrapped around and fixed to the top of the tower, allowing accurate blade positioning onto the shaft even under varying wind speeds. The turbine is released from slip joints using hydraulic cylinders and controlled vibration. After loosening, the structure is lifted, rotated toward the bow, and reinstalled on the support frame. Finally, the combined impedance measuring method is applied, marking a major innovation in offshore wind turbine installation. The CNC milling of a Pelton turbine runner is one of the most demanding machining processes in the hydropower industry. This complexity arises primarily from the intricate three-dimensional geometry of the turbine buckets, also known as spoons or gow. which are designed to efficiently convert the kinetic energy of high-velocity water jets into mechanical rotation. Each bucket features deep cavities, sharp splitters, compound curvature, and continuously changing surface orientations. The CNC machining process begins with the rough milling stage, which focuses on removing a large volume of excess material from the forged monoblock turbine runner. At this stage, the primary objective is efficiency rather than precision, as the machining must rapidly shape the solid blank into a form that approximates the basic geometry of the Pelton turbine buckets. Because the runner is manufactured from high-strength stainless steel alloys capable of withstanding extreme hydraulic loads, the cutting process must be robust, stable, and carefully controlled. During rough milling, indexable milling cutters equipped with carbide inserts are commonly used. These tools are specifically designed to handle high cutting forces and large chip loads while maintaining tool stability. The 5-axis CNC machine continuously reorients the cutting tool to reach deep cavities and curved internal surfaces within each bucket. This multi-axis capability allows material to be removed evenly from complex areas that would be inaccessible using conventional 3-axis machining. Coolant is applied continuously to reduce cutting temperatures, minimize tool wear, and ensure efficient chip evacuation from confined spaces inside the bucket cavities. Material is removed layer by layer while maintaining a uniform machining allowance across all functional surfaces. This allowance is essential to support subsequent semi-finishing and finishing operations without risking dimensional deviation. Tool paths during rough milling are carefully optimized to avoid abrupt directional changes, which could induce vibration, chatter, or excessive stress on the cutting edges. Even though the emphasis is on high material removal rates, dimensional awareness remains important to prevent overcutting that could compromise the final bucket geometry. Once rough milling is completed, the machining process proceeds to the semi-finishing stage. This phase serves as a transitional step between aggressive material removal and high-precision surface generation. Semi-finishing focuses on refining the bucket shape and bringing the machined surfaces closer to their final design contours. Compared to rough milling, smaller cutting tools are used, and cutting parameters are adjusted to achieve improved stability, accuracy, and surface consistency. During semi-finishing, the 5-axis machine plays a critical role by allowing continuous adjustment of tool orientation to follow the complex 3-dimensional curvature of the Pelton bucket interiors. Maintaining the correct tool angle relative to the surface reduces tool deflection and ensures more uniform material removal. This results in improved dimensional accuracy and prepares the surface for final finishing with minimal correction. An important function of the semi-finishing stage is the redistribution of internal stresses within the workpiece. By removing material more evenly and reducing localized thickness variations, This stage stabilizes the runner before finishing. This is particularly important for large turbine runners, where residual stresses from forging and rough machining could otherwise cause deformation during the final cutting process. Following semi-finishing, the process advances to the finishing stage, which is the most critical phase of CNC milling for a Pelton turbine runner. The finishing stage directly determines the hydraulic performance of the turbine, as it defines the exact geometry and surface quality of the bucket profiles. Even minor imperfections at this stage can lead to increased friction losses, flow disturbances, or inefficient jet impact during turbine operation. Finishing operations are typically performed using ball-end mills, also known as ball cutters. These tools are ideal for machining complex freeform surfaces because their spherical cutting edges allow smooth transitions across continuously changing curvature. Tool paths are generated with very small step-over distances to minimize surface scallops and achieve a high-quality surface finish. The resulting surface must be smooth and geometrically accurate to support optimal water flow behavior. Cutting speeds and feed rates during finishing are carefully controlled to reduce vibration and maintain a consistent cutting load. The CNC machine executes simultaneous 5-axis movements, enabling the tool to maintain a constant orientation relative to the surface normal. This ensures uniform surface texture and prevents tool marks that could negatively affect hydraulic efficiency. Special attention is given to the splitter ridge, bucket lips, and the deepest areas of the bucket cavity, as these regions play a crucial role in dividing and redirecting the water jet. The accuracy achieved during finishing depends heavily on advanced CAD and CAM software. Digital models of the turbine runner are used to generate precise multi-axis toolpaths that accurately follow the bucket geometry. CAM systems calculate optimized cutting strategies based on tool geometry, machine kinematics, and material characteristics. These systems ensure that the transition between roughing, semi-finishing, and finishing operations is smooth and geometrically consistent. Before machining begins, the entire process is simulated in a virtual environment. This simulation allows engineers to verify tool paths, analyze material removal, and detect potential collisions between the cutting tool, tool holder, machine components, and the workpiece. Collision avoidance is especially important during finishing, where tools operate deep inside narrow bucket cavities with limited clearance. During actual machining, continuous monitoring of spindle load, cutting forces, and vibration is used to maintain process stability. Tool wear is closely observed, particularly during finishing operations where even minor wear can affect surface quality. Tools are replaced or reconditioned according to predefined wear limits to ensure consistent machining results across all buckets of the turbine runner. In some cases, adaptive machining strategies are employed, allowing the CNC system to adjust feed rates automatically in response to changing cutting conditions. After finishing, the machined surfaces of the turbine buckets exhibit high geometric precision and a smooth surface texture. These characteristics are essential for minimizing hydraulic losses and maximizing turbine efficiency. The consistent surface quality achieved through CNC finishing significantly reduces the need for manual polishing and ensures repeatability across multiple production units. The final geometry closely follows the original hydraulic design, allowing the turbine runner to operate efficiently under high-pressure water jets. Through the precise execution of rough milling, semi-finishing, and finishing stages, CNC machining produces a Pelton turbine runner that meets strict performance, durability, and efficiency requirements for modern hydropower applications. In conclusion, the CNC milling of a Pelton turbine runner is a sophisticated, high-precision manufacturing process that combines advanced materials, multi-axis machining technology, and powerful digital design tools. The use of 5-axis CNC machines enables complete access to the complex internal geometry of the buckets, while staged milling operations ensure efficiency, accuracy, and superior surface quality. Compared to traditional casting methods, CNC machined Pelton runners offer higher hydraulic efficiency, improved structural integrity, and longer service life. As demonstrated in the video, this process plays a decisive role in producing high-performance Pelton turbines capable of converting the energy of high-pressure water jets into reliable and efficient electrical power.